Okay, so good evening, everyone. Welcome back again to week 7 of Basics of Semiconductor Microwave Devices course. I'm Shazan Bhatt, and I'm a direct PhD student at Applied Quantum Mechanics Lab in IIT Bombay. And this course is being offered by NPTEL portal, and the course instructor is Professor Digvijay Nath. And uh, So what we are going to cover today is the GaN, AlGaN, HEMTs, high electromobility transistors, and how they are going to manifest in microwave devices, particularly for high frequency, high power applications where maybe conventional devices fail to perform. Okay, so this will be today's. This is week 7. We are into week 7. So we have progressed into this particular topic. Now we are going to move into GaN, AlGaN HEMTs. We're going to study about substrate effects, something called as Johnson figure of merits, and we're going to study about the maybe N-polar and GaN polar as well as gallium polar and N-polar devices, and then we are going to solve some questions. So what I can see is that in this week there were many lectures. I can calculate, I can count, I guess 5 or 6 lectures. So it's quite a lot of material to cover. But in this week today we will be mostly dealing with the questions, maybe a brief recap or overview of what professor has tried to cover in this particular week. So this particular figure, I mentioned this particular figure here because of two reasons. The first is that you have been given the introduction about what GaN, AlGaN, HEMT is, and how does the two-dimensional electron gas come into picture. Okay, so I'm talking about when I talk about two-dimensional electron gas, I'm talking about this layer, which is a channel of electrons. I should say sheet charge per centimeter square. So it's a two-dimensional electron gas, and we have talked about how this particular two-dimensional electron gas forms, and what role does there is another layer which is not shown here. There is one more layer here, which is aluminum nitride. So it keeps the two-dimensional electron gas confined. It basically prevents the scattering and other effects. So you have a huge density of two-dimensional electron gas, and also this aluminum nitride is highly polar material. So it has a very huge piezoelectric coefficient that brings in more, I should say, charges into the two-dimensional electron gas, and you have a huge density of two-dimensional 2D gas. Okay. Now, what is this particular picture showing you is that you have a this is a typical GaN AlGaN structure. This is one device what we will be talking about. Okay, so this is silicon carbide substrate. So most of the time silicon carbide substrate is used, or silicon substrate is used, or maybe silicon nitride, not silicon nitride, silicon substrate may be used. Okay, but this is not, I should say, uh, a conventional silicon in 100 configuration. So it has some other in 111 configuration it may be used. So these are the crystal indices you might be aware about. And then there is aluminum nitride nucleation layer used because this particular for this interface to be a good interface for the lattice mismatch to be lower, we use the aluminum nitride nucleation layer, and then we grow the gallium nitride over it. And this gallium nitride is basically entirely not a same type of gallium nitride. So it's doped until, I should say, a certain thickness. It's doped highly, and up to the other part, it's basically intrinsic GaN. But by default, GaN is basically, I should say, unintentionally doped GaN is most of the time N-type. So you have excess electrons most of the time. So this can be doped, let's say, doped by silicon, it can be doped by carbon, it can be doped by maybe iron. So why do we basically dope this particular GaN? Let's say if this GaN thickness, maybe if I show you, if this GaN thickness is overall, let's say 200 nanometer, up to almost 100 nanometer, this particular layer is doped. Okay, so it's doped in order to basically suck the extra electrons which are present in the gallium nitride, because gallium nitride is unintentionally, it's almost n-type, so there are electrons present in here. So what these dopants do is that they produce traps. Okay, deep traps, particularly iron and carbon. They produce deep traps. So if this is gallium nitride, this is the conduction band of gallium nitride, this is valence band. So these produce traps here in the mid band region. Okay, so that those electrons stay there. And as a result, you get almost an intrinsic type behavior in this gallium nitride. That is what you basically want, because you don't want the electrons to roam over the entire gallium nitride. If that happens, you will lose the controllability over the channel and controllability over the field effect transistor, or switching on and off the device, and hence the microwave performance will degrade accordingly. So you just want the electrons to be present in this layer, which is the two-dimensional electron gas layer, so that whenever you apply, let's say, a negative voltage, it repels these, it depletes the channel, and you get an off state. Okay, but one more thing can happen is that there can be a conduction part via this particular thing, from source to drain via the gallium nitride substrate buffer. Okay, so that has all to be that has also to be prevented. So there are typical many cases which professor might have discussed what is the effect of the substrate, and even if you, let's say, could talk about this particular silicon carbide substrate, sometimes it's maybe sometimes its thickness is huge and you have a thermal issue. So in that case, you want to basically etch this particular or what should I call it, polish or remove this particular silicon substrate to reduce the thickness in order for the for better thermal management of the device. Okay, better thermal management of the device. So there are a lot of issues. Another thing that you might have seen in the lectures, previous lectures also, is that this particular length is going to matter, which is the gate to drain length. Why is it going to matter? Because it correlates directly with something called as breakdown voltage. So higher this, greater this length, better will be the breakdown voltage, and that's what you want. You don't want the device to get breakdown at lower voltage. You want it to break down at larger voltage. But there is a trade-off. What is the trade-off? If you go on increasing this particular length, if LGD goes on increasing, the delay basically increases. So as a result, your frequency suffers. So there is always a trade-off in these parameters, and it's up to the, I should say, what specifications you want. It's up to what are the characteristics you want out from the device. What is the performance you want out from the device? So accordingly, you can fabricate the device. But these trade-offs will be always there. Similarly, there will be this contact resistance from the source, contact resistance from the drain, and there will be channel resistance. These particular things have been covered quite well. And one important thing here is that these surface states play an important role, as you know that we have talked about in the maybe previous sessions, that these are the particular surface states from which the electrons basically come and settle at the interface of GaN and AlGaN. So these surface states, which is, let's say, this is aluminum gallium nitride, and we have a thin layer of aluminum nitride, and then there is basically something called as gallium nitride. This is gallium nitride. So you know that this is the Fermi level, and electrons from these are basically donor type states, donor type states, and you know that electrons are going to come from these donor type states. They are going to settle at this particular place whenever you fabricate the device. So that this happens during the fabrication process, and whenever you kind of make these layers, whenever these layers are separated, let's say this is gallium nitride, this is aluminum nitride. So this is the conduction band, this is the valence band. Similarly, this is conduction band, this is valence band, and this is, let's say, AlGaN, aluminum gallium nitride. This is conduction band, this is valence band. So whenever you kind of combine these materials, it basically attains a single Fermi level. Attains, I should say, it attains an equilibrium, means it has a single Fermi level. So these electrons basically come from the donor state, they settle here, so that the overall the Fermi level should be aligned. Okay, just like the water level. It whenever you have a difference in water level on the two sides, and you open the container to the water level in both the containers should be equal. So it's just like that. Okay, so I've discussed it many times in the previous lectures also. So these donor type states basically play an important role. Now what happens is that these donor type states can donate the electron to this particular layer, and as a result you have a huge concentration of electrons at this particular position. Now sometimes what may happen is that if you apply a huge negative voltage, let's say a huge negative voltage of maybe -6 volts or -5 volts, these electrons basically from the metal uh, can go to these donor states and they can neutralize them. As a result, it is going to affect the depletion width at this particular position. So that is again another effect which basically comes because of it. So that's why what you do is that you go on applying a silicon nitride capping basically a layer over it, particular passive, something called as passivation layer, silicon nitride passivation layer, and that is what is done to in order to reduce the surface induced collapse, or in order to protect these particular traps. And again, these particular this is also going to have implications in, or I should say, trade-offs. Whether protecting these traps is going to improve the device performance or not, there are certain trade-offs in it also. Okay, now what else is basically important? And let me see. Yeah, so this is the device. So typical devices now, if you talk about this is the typical device. You have this is the substrate. Let me draw it. This is the substrate. When I draw it like a wavy curve, so it means it's not drawn up to the scale, or it's not planar. Okay, there are a lot of non-uniformities because it's the backside of the substrate. So let's call it silicon nitride substrate. Then you have a nucleation layer. This is the nucleation layer. You have the nucleation layer, which is most of the time aluminum nitride. Then you have the gallium nitride, and it may so happen that this part may be intrinsic gallium nitride, this part may be doped gallium nitride. Okay, intrinsic means I should say unintentionally doped. Okay, but this is intentionally doped gallium nitride. It may be carbon doped, it may be silicon doped, or iron doped, so that it can trap those extra electrons which I discussed. So as a result, what happens is now we have another layer which is aluminum gallium nitride, AlGaN layer, and then we have basically the source contact, we have the drain contact. Okay, this is the source contact, this is the drain contact, and we have the metallic contact present over here. This is the gate. So this is source, this is gate, this is drain. And now what happens? You also know this particular distance, which is basically the gate to channel distance. Where is your channel? Now we forgot one of the main important things, which is aluminum nitride layer present at this particular position. This is aluminum nitride layer. This is approximately 1 to 2 nanometers thin. It's very thin layer. Okay. Now what happens is that this particular gate to channel length is very important because it determines how good can your gate control the channel, because your 2D electron gas is present somewhere here. So this is the 2D electron gas. So what happens is that what happens? So basically your wafer is something like this. Let me extend it. This is your wafer. It's circular. It's a disc. So we are basically cutting a section of it. Okay. And these your contacts are made something like this. So these are your contact pads. So this is a three-dimensional view. Maybe sometimes you may get confused what's going on. Okay, so we are looking at this end from this side. We're cutting a cross section of that particular sample, particular disk. So so now what happens is that if you have this particular gate to channel length is going to be very important. Why gate to channel length is important? Because it's going to determine the transconductance, which is the variation of the drain's current with respect to the gate voltage. Okay, so how better can a gate control the channel? Okay, because it's capacitively coupled. That's why it's a field effect transistor type, because it's capacitively coupled. You are applying some voltage here, let's say negative voltage, that is coupling capacitively. That electric field is basically, that field is being created, that is repelling or depleting this channel, so that this channel is basically getting depleted. Okay, so that is the coupling we want, and you want this capacitive coupling to be large so that you can control the transconductance parameter. And and also basically if you for example if you look at these particular ends, which are the source and drain ends, you call about these particular source and drain ends. Now what happens is that you want a better contact to be better contact. What do you mean by better contact? This should be ohmic. That means it should follow V equals to IR. The current voltage relationship should be linear. Okay. It should not be Schottky. Schottky looks something like this. Okay, this is Schottky. And you want this ohmic so that the contact resistance is reduced. Now, how do you do it? You make something called as maybe a titanium contact and titanium nitride or titanium alloy, so that what happens is basically that particular titanium goes and reacts here with this particular layer, and they basically form something called as titanium nitride species. And because of something called as nitrogen vacancies, they have large number of electrons. Okay, so when you have large number of electrons there, it almost approximately becomes the n-type contact. Okay, so there is a lot of physics involved basically there, and it's almost entirely, it's again the contact resistance comes into picture, and it's still the open area of research. People are still working how to reduce the contact resistance. So that basically is about this. And now what you have. So this is the particular via hole we have talked about most of the time. So this is basically a via hole where you have kind of etched this layer particularly, and it's filled with the metal so that you have a common ground plane. And it basically reduces the source inductance, because inductance is proportional to the loop area. So if you reduce the loop area through which the current is flowing, you can reduce the inductance, basically the source inductance. Source inductance. So if you talk about this device here, if I just add one more page, if you have, let's say, if you have a device like this is substrate, this is aluminum nitride, gallium nitride, aluminum nitride, not this, aluminum nitride, and this is AlGaN. So this is AlGaN, so this is GaN. Okay, and other layers you know. So what is basically done is that if you have a source here, you have a drain here, you have a gate here, this particular layer is etched to reach the source thing, to make something called as via hole. Okay, so this is the via hole, so that you can have a common ground. Okay, so it basically comes from bottom of the wafer to the top of the wafer. Okay, so that has been particularly discussed in also previous lectures about these via holes. They have been commonly discussed a lot of times. Okay, so this is a typical structure of a I should say monolithic integrated microwave circuit. It has all the things on it. It has a pad, it has a high electromobility transistor, it has an air bridge. These are basically the air bridges, which are just like a metal flaps, and they are suspended in the air. So there is nothing in between it. And they are suspended and connect one end to the other. That's called as basically air bridge, and they are very difficult to fabricate. Okay, so sometimes because they are almost like a hanging structures in this particular device. Okay, so now what next? Okay, so now let's look at the questions. Let's look at the first of the questions. So we will discuss about the questions, because a lot of material has been covered in this session, and it's quite I should say uh, unrealistic to cover entire 6 days of material. So we will discuss in the questions, we will discuss deeply about what are the concepts related to that questions. So first of all, there's first question. So we have to consider two AlGaN HEMTs. Okay. So HEMT X has a barrier thickness of 25 nanometer, and HEMT Y has an AlGaN thickness of 30 nanometer. So don't get confused here. They have mentioned AlGaN thickness, and here they have mentioned barrier thickness. So it's one and the same thing. AlGaN acts like a barrier. Okay, because if this is gallium, this is simple AlGaN GaN HEMT. Where right now we are not considering the aluminum nitride layer. So this is basically the barrier, because it acts like a barrier to the 2D electron gas. 2D electron gas is present here. If this is Fermi level, then the 2D electron gas is present here. This is the 2D electron gas. So they are saying you have two HEMTs. So you have HEMT X, you have HEMT Y. Okay, so now what? So for this HEMT, you have the barrier thickness of 25 nanometers. For this, you have the barrier thickness of 30 nanometers. Okay, and you know that gate is present on this side. This is the gate. So you see what is going to happen now. Both HEMTs have same two-dimensional 2D electron concentration at equilibrium. This could perhaps be due to different aluminum composition in the aluminum like AlGaN barriers of the two HEMTs. Okay, so it's saying that both have the NS here is equivalent to the NSX is equivalent to NSY. NSX is equivalent to NSY, which is basically the 2D concentration. They are same. And it's saying that it can be done because of varying aluminum composition. Maybe this is aluminum 0.2, gallium 0.8, N, okay, or maybe this is aluminum, let's say 0.3, gallium 0.7 N. So you can have a same 2D electron concentration by varying the composition of this. Now, what we have to say? We have to select the correct statement. So we have to read each and every statement first. Both HEMTs have the same threshold value and same transconductance. Okay, it's saying both HEMTs have same threshold value. That's not going to happen because you have a different barrier thickness, and you know that barrier thickness is going to affect the controllability of the gate over the channel. Because if this is more thick, this is more thick, then gate has less control over channel, because that is going to happen. Because if you increase the thickness, because you know the capacitance is epsilon divided by thickness. Okay, this, let's say this is thickness of the barrier. If you increase the barrier thickness, capacitance coupling will reduce. That is as simple as that from the electrostatics. Can you please turn off your audio? Excuse me. Okay, thank you. What is going to happen is that the capacitive coupling in case of the, I should say, thick barrier layer is going to reduce. Okay, so now what is going to be the impact on the transconductance? And you know that if you have the capacitive coupling reduces, that means the gate is going to lose the control over this particular channel, which is the 2D electron gas. Okay, now that is going to affect the transconductance. Transconductance is going to go down because it is the change in the drain current with respect to the gate voltage. So if your transconductance goes down, and it's going to affect the device performance. Okay, so now what are the other effects? So now we have seen that the transconductance goes down. So the what is going to happen for the thicker one, the transconductance will go down. So HEMT X has higher peak transconductance. HEMT X is this one because it has lower, I should say, it has thinner barrier layer, so its transconductance will be more. That means GM for X will be greater than GM for Y. Okay, this particular thing seems correct. And it has less negative threshold voltage than HEMT Y. And it's saying that it has less negative threshold voltage. Now, why would this have less negative threshold voltage? Let's see whether this option works or not. So less negative threshold voltage means that you have to apply lesser voltage in order to pinch off the channel. So as you, if this is drain versus VGS characteristics, not VGS, it's VDS. Let me drop this. If this is VDS, okay. So this is VGS increasing negative in the negative direction. So let's say this is -1 gate voltage, this is -2, -3. So as you go down, the channel pinches off, the channel turns off. Okay. Now, why is it going to be lesser in case of the first one? Because it is capacitively more coupled to the gate. Okay, this barrier, this particular barrier here is smaller, this is larger here, so it's capacitively more coupled to the gate. So you will naturally require lesser threshold voltage in order to deplete this particular channel. So when you will apply the, so in this case, when you will apply the negative voltage on the gate side, this gate side is going to go up. What I will show it on the same figure maybe. So when you will apply the negative voltage here, this gate side will go up, the electrostatic potential energy of electrons go up, this particular thing will go like this, and you will have the depletion of the channel. So the band diagram will look like the red dotted line. So you will have depleted channel here. That means depleted of what? Electrons. So electron concentration reduces. So that's what is going to happen. So you will have naturally less threshold voltage or the gate voltage required to deplete the channel. So that is the overall concept of this particular question. Okay, so now I've talked about in the previous slide, shorting all the gate terminals via the something called as via holes basically is going to reduce the source inductance. And this has been basically discussed in the previous assignment also. It has been almost asked 3 to 4 times in this session. We have talked about the via holes in this particular slide, and we have talked about via holes here also. So that basically reduces the loop current, and that is going to affect the source conductor inductance also. Okay, so now moving on to the next question. The impedance of a transmission line on a wafer is affected by. So which transmission line are we talking about? So you have, let's say, a source pad, you have a drain pad, you have a gate pad, and you have a gate line. Okay, that is going to come from the gate. Now, this basically you can basically think of these particular things as a transmission line. Maybe might have a picture. Okay, yeah, something like this. Let's say you have a GaN HEMT, you have a gate, and you have a line coming in, you have a source, you have a drain, maybe as one of it is grounded. And what is going to basically happen is that, so this is the via hole which I was talking in the previous slide. So what is going to happen at, like, whenever you apply some input RF, so you expect some output RF power to get out. So that is basically the concept of the transmission line. You have a input port, you have an output port, and you have incoming waves, you have outgoing waves. So this is RF in, this is RF out. So it has naturally certain impedance. This particular circuit has certain impedance. And now what does that impedance depend upon? That is what the question is asking. So this impedance basically depends upon the width of the transmission line, and it depends upon the thickness of the barrier layer. Why do these two important things matter? Okay, so what happens is basically I told you, if you have a AlGaN layer and if you have a GaN layer, and you know that you have a two-dimensional electron gas present here, and the gate is present at this particular region. This is the drain, not like this. This is the drain, this is the source. So this particular distance, the gate to source distance, and this particular system distance, gate to drain distance. So gate to drain distance is greater than gate to source distance. So it has different reasons about the breakdown as well as the thermal management reasons. Let's not go into that. But this is, let's say, this is the substrate. But what's going to happen is that I told you this particular distance is going to matter, the gate to channel distance. This is the channel. Okay, so that is going to basically come as a impedance of the transmission line, which is some R plus JX, where this X can be it can be XC, which is 1 over J omega C, or it can be XL, which is omega L, not J because I've included. Okay, so it's a complex quantity. And this impedance basically, because it depends upon the resistance, so these dimensions are going to be important in the transmission line of a wafer, particularly. Whenever you talk about these microwaves, you are talking about the microwaves moving through these gate, moving through these through these particular channel, through these particular layers, something called as bus bar, which is coming from the gate. Okay, so now you have to invoke the microwave concepts. You feed in certain signal, input signal, you want certain signal out, maybe you have certain phase differences in the waves, because you are talking about electromagnetic waves of the order of maybe 100 gigahertz frequency or 50 gigahertz frequency. So you are feeding some input, you are getting some reflected input, and you are getting some transmitted input, and there is an impedance, which is the input impedance, which comes into picture. That's what also I discussed in the previous session. This input impedance or impedance matching is really important in these. If you want certain thing, let's say this is input wave coming, there will be some reflected wave, there will be some transmitted wave. Then at this particular interface, there is basically a uh, something called as impedance mismatch. Impedance mismatch. And I gave you a simple example in the previous lecture about a refractive index. If this is a medium with refractive index n1, this is a medium with refractive index n2, this is interface, then if a light comes into this, it gets reflected, it gets transmitted. It's the same phenomena. Okay, it's the same phenomena in this, because we're dealing with the microwaves here. So here the reflection coefficient is basically n1 minus n2 over n1 plus n2, approximately. You might have studied from your high school physics. If the wave is basically normally incident. Otherwise, there are certain angles which come into picture, and certain boundary conditions. Okay, so similarly, you have the reflection coefficient and transmission coefficient that is going to be determined here, and they are going to be dimension dependent. That's what basically the question is about. So that's all about this question. You don't need to think more about this question. Now, what is another question? We have another question as that is improvement in thermal management in the GaN AlGaN structures done by. So this particular question, it has multiple answers. Maybe they might have shown single answer, but it can be done by via holes. It can be done by thinning the substrate. Why it can be done by using these is because let's say you have a you have this particular structure where this is substrate, this is GaN. Let's forget about nucleation layer right now. Nucleation layer is somewhere here, which is aluminum gallium nitride, aluminum nitride. This is AlGaN. So this is source, this is drain, this is gate. Okay, so what happens is that here you have a 2D electron gas, and you are applying certain microwave input here. You are grounding this terminal, you are applying another voltage here, so that if you are applying positive voltage here, the electrons are moving in this direction, the current is flowing in this direction as per the convention. Okay, now you are dealing with the huge power. You're dealing with the power of the order of 50 watts, maybe 60 watts. So this is a lot of power. And there are I square R losses, which is basically the heating losses in the devices, heating losses. And where is that heat going to go? That is obviously going to remain in the gallium nitride. But one important thing is that one advantage of this particular HEMT is that aluminum, which is this layer, AlGaN structure has huge thermal conductivity. That means it will take most of the heat out. But where is that heat going to go? Definitely there has to be a heat sink used. But heat basically spreads throughout uniformly in the entire direction. So it will basically let me show it. It will spread, the heat will spread along this particular layer. Yeah, that's what I'm trying to explain. This can have this basically this question has multiple answers. This thermal management can be done via creating via holes. It can be done by thinning the substrate. It can also be done by reducing gate to drain distance. Okay, so that's what I'm trying to say. Maybe they might have shown you the only option as this, thinning the substrate, which is absolutely correct. But this can also be done to these two options can also be done to reduce the thermal management. That's what I'm trying to explain. Okay, so that's what I'm trying to explain. Yeah, that is the problem. That's what I'm trying to explain. So what they have done is that maybe whoever has set the paper has not maybe thought about creating via holes can help in thermal management. Because even if you watch the professor's lectures, not even professor's lecture, if you think about it, the via hole concept about making a hole from top to the bottom and filling it with metal. So whenever you are filling it with metal, it's a very high thermal conductive system. So it's going to take out the heat also. It's going to help in the thermal management. Hmm. Hmm. Huh. Right, right. Hmm. Okay. Okay, listen to me. Just okay, thank you. I got it. I got your query. Basically, what you should do is that you should write to NPTEL portal who actually are managing it, because this is not directly under our control. Whatever they might have said there, you should talk to them that if there are multiple answers to a particular question, then they should allow it to basically opt for those answers. Okay. Because I can see. Mhm. Correct. Yeah, I got it. Yeah, I got it. You have a circles here, so whenever you have a, let's say this like this, something like this, squares, then at that time you have a multiple answer, just like the multiple answers for this is A and B. But what I'm telling basically is, basically the thing is that on their NPTEL portal, they have the correct option given as this particular part only. So that's why they have given the circles here. So they are expecting you to give only the answer as this. But I'm arguing about that these two things can also be done in order for the better thermal management of the device. Maybe whoever has said the paper has not thought about these two options. Or if you are basically having doubt that these two should also be the answer of this particular question, or I have basically in previous lectures previous lectures mentioned that there should be multiple answers. You should directly write to the NPTEL that you should correct the this particular questions in this particular quizzes, so that people should not face problem. Okay, okay, okay. So that's about this particular question. And again, so going to the other reasons is that how basically this particular distance is also going to this particular distance basically can also help in thermal management, because the heat is overall produced whenever you are applying the certain high, I should say, RF signal to the gate voltage. So there is also the heating region near this particular thing. So whenever there is basically if you just solve the heat equations, the governing heat equations in any of the simulators, whether it's TCAD or any of the simulators, you see that there are these hotspot patterns basically formed whenever you apply the gate voltage. And uh, by simple, I should say, physics, there was a in our group, I remember there was a research done that particular that lab mate basically showed that if you just modulate this gate to source distance, it is going to have a better device performance and thermal management compared to that of if you have a gate exactly in the middle. Okay, so these are again the open research problems, but they are all possibilities of that they can be the answer of this question via holes and reducing the gate drain distance. Pardon me, just this is gate to drain distance. I thought it's gate to source. So this cannot be, this is not the answer. Gate, if it is gate to source distance, then that is the answer. But via holes is definitely the answer. That also helps in the thermal management of the device. Okay, so what next? So it's not preferred to bias the gate at high voltage, high positive voltage. Why? So it's quite simple. If you have a this is gate, if you have a AlGaN structure, and this is AlGaN structure, and we are not mentioning here the aluminum nitride layer here because it's 1 to 2 nanometers thin, and it may the band diagram may look something somewhat like this if there is aluminum nitride, somewhat like not like this. If this is aluminum nitride, this is AlGaN, this is GaN, so this will look like this, and this will look like this. Yeah, this will be the exact band diagram, and this will look like this. So this will be the band diagram if there is aluminum nitride. So right now we are not considering the aluminum nitride layer. We are ignoring it for the simplification purpose. But all of the concepts will apply to the aluminum nitride layer also, having the actual structure we are talking about. So it's saying that if you go on increasing the gate bias to the positive values, because this is a depletion mode depletion mode transistor. That means you have a channel here, the 2D electron gas. You have to deplete it. You have to make it go away from the channel, go away from the interface. So for that, you apply the negative voltage so that you can capacitively repel these or deplete this particular region. Now the question says, what happens if you apply a positive voltage and you go on increasing the positive voltage? So if you see the curves, the ID versus VDS, the curves look something like this. I should start from the top. This is looks like something like this, and you have the VGS, which is gate to source voltage, increasing in this direction in a negative fashion, so that here the channel is almost pinched off, almost entirely depleted. It's a off state. It's a off state. Now, what happens if you go on increasing it in a opposite direction? It's saying in the opposite direction. That means VGS increased in positive direction. If you go on increasing the VGS in positive direction, it will be catastrophic for the device. Why? Because you are going to modulate this particular barrier, and there will be huge leakage currents flowing through this. That's what you don't want. If you have the current flowing, it will reduce the capacitive action. Okay, because you know that the charge is capacitance times voltage. Capacitance is charge over V. So if you lose charge, you will lose the capacitive action. Basically, the current will flow in this direction, which you don't want. If the electron will flow maybe in this direction here, you will flow the current in this direction, which will be the gate current. That is very detrimental to the device. You don't want the device, you don't want that this particular component to flow. So it's definitely going to alter the band diagram. So if this is the band diagram, why am I drawing like this? If this is the if this is the band diagram before application of the positive gate voltage, then what is going to happen if you apply the positive here? Positive basically pushes the Fermi level of the gate. or what you call as conduction band. It's one and the same thing, but because it's a degenerate system, so it pushes it down, it lowers the electrostatic potential energy of electrons. This will come here, this will go here, and this will come here. This will be a huge barrier. So this may include this may basically cause the tunneling of those electrons and other things. And this can also happen if you apply huge negative voltage. So that we have basically talked about in the previous cases. But you see that this particular barrier will increase. I should say the confinement will go on increasing, and there will be huge two-deck density because now the bending has increased. Okay, so the two-deck density will also go on changing accordingly. So the diode will turn on, drastically increasing the gate leakage. So what diode is he talking about? He's talking about this diode. It is a diode. Basically, it's a Schottky diode, because this is the Schottky barrier, 5B, this particular barrier. Okay, so it will turn on. So when it turns on, the current will flow and it will be detrimental. You don't want the gate current to flow. You just want it to control the channel capacitively, electrostatically, using the electrostatic fields, not the currents. Okay, there's a difference. Okay, now consider moving on to the question 6. Consider an AlGaN GaN HEMT which exhibits severe current collapse under the drain lag condition. Now, what is the current collapse? Let's maybe now it is saying that if you where it is go if you have a if you consider a GaN AlGaN HEMT which exhibits a severe current collapse. So the current collapse is if you have a drain current, if you have a gate drain voltage, and the curves look something like this, which I have been showing you previously. And this particular thing is something called as knee voltage. Up to this is something called as breakdown voltage. Breakdown. So you see that those currents basically start to droop when you go beyond certain drain voltage. Okay, and there are several reasons for it. Professor might have discussed about it so deeply regarding the basically something called as drain lag condition, wherein what you do is that if you have a gate, you have a drain, you have a source, you apply a pulsed signal to these particular things. Let's say a -6 volt here or 20 volt here. So you start applying the pulse signal. Why do you apply the pulse signal? And what happens because of it is that you apply the pulse signal as on and off, and this is the on region, this is the off region of the pulse signal, and usually the off region is huge, of the order of maybe 100 microseconds, and this thing is on is maybe of the order of 10 microseconds. So you see the duty cycle, which is basically the time it is on divided by on time plus off time. So basically it is on time divided by total time period, which is the total time period is this thing, T on plus T off. So duty cycle is basically how much time it remains on to how much time it remains off to the total time period. So it's very small. Okay, so now why we do it is that because in this particular region we want the heat to get dissipated. So because heat dissipation takes some time because it's a slow process. If it takes place via phonons, it takes place in a metallic system, it takes place via electrons, but it takes place mostly with the help of phonons. So it's get dissipated, and it's a very slow process. Thermal conductivity, thermal conductivity. It's a slow process, and there is something called as thermal resistance. There is something called as thermal diffusivity, and these are all slow processes. That's why you require the device to cool down at least during this pulsed operation, so that you can cool the device and you can give this. This again helps in the better thermal management of the device when you are testing it, when you are characterizing the particular device. So now that is basically the this particular condition, and this implies that breakdown voltage of HEMT will be significantly low. The output power will be low at microwave frequencies. So what is it asking? So which exhibits severe current collapse under drain-like condition. This implies that breakdown voltage of HEMT will be significantly low. Output power will be low at microwave frequencies. Yeah, so this is going to be the answer. Why it's going to be the answer? Because I showed you that there will be droop in the current. So if the current drops, what is the output power? The output power is ID times VD. So ID decreases, this is going to be reduced, which is the output power will be low at what? At microwave frequency. That's what we are basically dealing with. So because of this current droop, current collapse, that is going to be that's going to cause the severe output power to reduce. Just give me a moment. I just have to. Okay. Okay. Now what? Now moving on to other question, we have for ohmic contact formation. Yes, I talked about this ohmic contact formation here. We did talk about, yeah, in this particular slide. Yeah, in this particular slide here. So what happens basically? Where is it? So for the contact formation, you want the ohmic contacts to form. Now, where is it? Yeah, you want the ohmic contacts to form. So you have the, let's say this is AlGaN layer, this is GaN layer, and these are the contacts. Source, this is the drain. And you use ohmic contact formation, AlGaN, the metal pads needs to be annealed. And you use titanium, aluminum, this particular stacking of the metallic layers. And why is it done is because if this is the lower layer is titanium, then there is aluminum, then there is nickel, then there is gold. Okay, this is the stack formed in a particular ratio. There is a particular ratio, and most of the time fabrication people know it, just like a recipe. And nickel is there to prevent the gold to get diffused. Gold is on the top because it's inert, so that metal stack does not react with the ambient atmosphere. And then these are very high conductive, I should say, metals. And the titanium, what titanium does is that is it's the bottommost layer. So the 2D electron gas is present here, and there is aluminum nitride layer also, which I have not shown. Aluminum nitride layer is present here. So the titanium reacts with this aluminum nitride and it forms titanium nitride compounds. And what happens is that there is in this particular there is something called as nitrogen vacancy. It's a very deeper concept. Nitrogen vacancies basically hold excess electrons. So electron concentration is boosted up in this region. So that is what basically you want. If you have a huge electron concentration in this region, electron concentration increases, so your contact resistance will accordingly drop because it will almost behave like a metal. So that's what you basically want. So these titanium nitride X compounds, which are something called as titanium nitride spikes, makes a contact with the 2D electron gas. You can see that whenever it reacts, because aluminum nitride is usually of the order of 1 to 2 nanometers. It's very thin. So it directly makes contact with the 2D gas. It's just like a metal in a contact with another metal. Because 2D electron gas is almost like a metal sheet. Okay, not exactly like a metal, but it's almost like a metallic sheet because of huge concentration of electrons, the two-dimensional confinement. That's why it's called as two-dimensional electron gas. Just like it acts like a electrons in the metal. Just like electrons in a metal are like the gas molecules. If you have a metallic sheet, then you have electrons. They just behave as a free sea of electrons. And you can apply the laws of whatever you apply for the gas molecules. You can do the same physics here. That's why they are called as electron gas. Okay. Now, that is what basically is the answer of this question. So for making the better contacts, for making reducing the contact resistance, you do this particular stacking in order to make high concentration of electrons near this particular region so that you have a lower contact resistance. Okay. Now, what are the other options in this for better metal adhesion to the surface to improve ohmic contact, for metal surface morphology, which improves contact resistance to reduce the gate drain lag? No, it's not going to affect the gate drain lag, definitely not. Yeah, because that is dependent upon this particular distance. If this is gate, so this is LGD, so that this particular distance determines the gate to drain lag. It determines the breakdown voltage. It determines the frequency. It determines so many of lot of things. This particular distance is one of the most important distance in this particular entire structure. And this distance, the gate to channel distance and the gate to drain distance. So all of these dimensions are really important, and the fabrication people have to take care of what are the dimensions, and accordingly they can get a performance out from this device. Now, what is the other thing? The for ohmic stack, the role of nickel is, I think I told you here, nickel is there to prevent the gold diffusion into the aluminum. Yeah, that is what is the basic role of nickel. So these particular stacking is done so that you have a multiple layers, and you can have better control electrostatically over the particular channel. So this basically contact stacking has been discussed in, I guess, lecture 4 or lecture 5 deeply, and I've talked about it almost for half an hour. So so again, this I told you that this particular gold is used on the top because this is inert. This is used so that the gold does not diffuse into the aluminum, and these particular metals are very high electrically conductive, so that you can have a better or lower contact resistance. And then titanium nitride again lowers the contact resistance because of these something called as nitrogen vacancy centers. And nitrogen vacancies are basically a very deep. It's a hot topic. It's a hot topic, not in here, but it's a hot topic in something called as quantum sensing. Maybe you might want to get interested sometime. So quantum sensing uses these nitrogen vacancies in order to something called as using microwave, they control the spin of the electrons in these nitrogen vacancies. So the nitrogen, if this is let's say a structure, and if you have a vacancy of nitrogen here, they basically have electrons. So nitrogen vacancy means it is a nitrogen atom replaced in a lattice by some other atom. It is something like if you have a gallium, nitrogen, 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 nitrogen. If this nitrogen goes missing, then this is basically a nitrogen vacancy, and it hosts electrons. Okay, an electron can be upspin, electron can be downspin. Now, if you have certain microwave frequencies, they can turn the spin of these upside down, and you can play with it, and you can have basically a instrument, something called as quantum magneto magnetometer. It basically measures the magnetic field of the order of I think nanotesla. Okay, this is a very small magnetic field. Okay, so this is a one of the instrument that one of the labs at IIT Bombay has made, and they mostly work in, this is something called as quantum sensing, so they mostly work on it. And where do you use this nitrogen vacancies of the order of this nanotesla magnetic field? So you use to detect the anomalies in the Earth's magnetic field, and how does Earth's magnetic field change, the magnetic field inside the maybe a living cell, bacteria. So this is a whole lot of topic. So nitrogen vacancies is a very deeper topic. So this is from this particular thing. What is other thing? Yeah, this particular thing now. Now we move to the question 9. So we have to consider two AlGaN HEMTs whose capacitance profiles are given with respect to the gate bias. Okay, so we are given two capacitance profiles. I can see that capacitance of A is greater than that of the capacitance of B. So this is gate to source capacitance. Okay, so now what is going to happen? Assume that both have the identical device dimensions and have same parasitic elements. Okay, pick the correct statement. So we have to choose the correct statement. Now, what is going to happen if you have a better gate to this capacitance? Let's say this is gate, this is GaN, this is 2D electron gas. So if you have a better capacitive coupling, you know that naturally your GM is going to be more. Why? Because GM is the variation of the drain current with respect to gate to source voltage. This more means better control over the channel, over the 2D electron gas channel. Okay, so naturally the transconductance is going to be better. Okay, if you have a greater capacitance. So the HEMT A has higher transconductance than the HEMT B. Okay, the other options does not match. What are the other options? HEMT B has higher transconductance than A. Both HEMTs have the same transconductance. Okay. Yeah, this sounds logical. Right. Let me still check whether I have solved this particular problem. Where is it? Yeah, correct. Yeah, this sounds logical because of the capacitive coupling. Exactly. So now what else? We have to use the same question again. Continuing from the above question, the figures shown below are the CV profiles as well as velocity field profiles. So this is a typical velocity versus electric field, where this basically gives the information about the critical electric field. beyond which the velocity gets saturated to a velocity called as saturation velocity. Your electron velocity cannot increase beyond this velocity. Okay, and this concept I also have discussed in the previous session. This saturation velocity is something related to terminal velocity of a raindrops when they are falling from the sky. So they attain a constant velocity because of the continuous drag of the air on the raindrop. They both two balance and it attains a terminal velocity. That is the same concept as saturation velocity because there is a drag inside the atomic system, the lattice drag, the impurities, the defects. So you have this velocity saturation beyond certain critical electric field. That's again I have discussed in the previous sessions. So now what we have to see here is the as well as velocity profile. Okay, the ratio of 2D sheet resistance is now what is the sheet resistance? Now we have to see the 2D sheet resistance of let's say HEMT A versus 2D sheet resistance of HEMT B. Let's talk about the concentration first. If we talk about concentration, 2D concentration of A and 2D concentration of B from this particular plot, what do we see? We see in A there is a larger, I should say, velocity. Critical velocity is reached earlier as compared to that of the B. So you have a larger critical field here. The critical velocity is same in this particular thing. The critical velocity attains the same value, but they have a different critical field values. Okay, for the HEMT A, lower critical field gives you the maximum saturation velocity. That means it should have higher concentration of electrons. So concentration of 2D charges, 2D sheet electrons is more in A compared to that of B. So if you have more concentration of in A than that of B, that naturally means the resistance of B or resistance of A should be less than resistance of B. Okay, so this is the exact thing. This is the exact concept they wanted you to understand from this particular picture. And then as per it, what is going to happen is that you have now to calculate the ratio for HEMT A to HEMT B. So for HEMT A, it will be greater for HEMT A, whatever. For this is RSOA over RSB would be less than 1. That means this should be greater. That means this option goes, this option goes, not this can remain. This option goes. Then only two options remaining are 1 is to 2 and 1 is to 4. So basically, this particular thing will depend upon critical electric fields. Okay, and you know that critical electric fields is given here. You have a 20, you have 10. You can basically compute it. It will be approximately 10 over 20, so you get 1 is to 2, which is the RSA over RSB. That is approximately equivalent to 1 is to 2, and that makes sense because the sheet resistance theoretically we saw that for the B it should be greater than that of A. So that naturally omitted the first and the last option, and the only option remaining were two, and then you have to compute it using the field ratios of these particular two HEMTs. That is one picture. What is the other thing in this question asked? Okay, that's it from this question. Yeah. Okay, so again, considering the HEMTs, assume that they have the same critical electric field. Okay, if they have the same critical electric field, that means this line is going to look again like this here. That is what they mean if they have the same critical electric field. What is going to happen is that JFOM. What is JFOM? Is something called as Johnson figure of merit. Johnson figure of merit. I hope the professor has discussed about it. So it's just like if you have maybe a breakdown. Let's not call it breakdown. Let's call it critical electric field. The critical field versus the frequency curve. It looks something like this. So they are inversely related. You can just do basic maths in order to show it. You can basically show that omega times t tau is 1, and you can use tau basically is the gate length divided by maybe your saturation velocity, and then you can play with it. You can write tau, you can write omega as 2 pi times frequency. You can play with it here and there. You get an inverse hyperbolic relation, which is proportional to which is inversely related to each other. So it says that as you go on increasing the frequency, your critical field lowers. So now what is going to happen? If you have the same critical electric field, if you have same critical electric field for both of these HEMTs, that means let's say for one HEMT A, red curve, for HEMT B, this is a brown curve, and they have same critical electric field. If they have same critical electric field, that means they are going to have a same Johnson figure of merit. Okay, Johnson figure of merit is basically this critical times the some frequency is equivalent to some constant. This is the Johnson figure of merit. So if you have same critical electric field and this particular point is same, then it will be having same the frequency which can be supported by it, which is the microwave frequency. So that means it will be having the same Johnson figure of merit because the critical field for both is same. So I hope the answer is this. Both HEMTs have the same Johnson figure of merit. So this is the answer of this question. And this particular concept has been discussed in, I guess, lecture 5, maybe, if I correctly remember. And it has a simple derivation. Basically, you can just shuffle these equations. You will get to a equation with the critical electric field and the frequency, which will be some equal to some constant. And this constant is basically some dimensions. Some dimensions. You can just do this exercise maybe, or maybe professor might have shown it. All right, moving on to the next question. Consider a HEMT with self-aligned gate. Okay, the spacing self-aligned gate and the spacing between the gate to source and gate to drain are very small and it's equally spaced such that the excess resistance can be ignored. Okay, you have a structure, you have a AlGaN, you have source, you have drain, you have gate. So these spacing are equal. You may ignore the contact resistance and other parasitics. Okay, you have to ignore the contact resistances and parasitic or channel resistances, other things. The gate length is 500 nanometer. The velocity field curve is given, which is velocity versus field. So this particular value is the saturation velocity. This particular value is the saturation velocity. This is the critical electric field, and this is the saturation velocity. So from this curve, you can get the saturation velocity. Now, where are you going to use it? What is the thing we have to find? A drain bias is applied with the gate voltage being at zero. The intrinsic unity gain frequency for this HEMT is. Okay, so whenever we talk about intrinsic, we always talk about this part. This is the intrinsic device because this particular thing, gate length, determines the overall delay, overall frequency. The other things, these particular things which are external to it, these are extrinsic parts. Source and drain, they are extrinsic to the device. The main thing is the green one, which is something called as intrinsic part of this HEMT. So now what do we have to find? We have to find the unity gain frequency. So you can use simple maths because if you compute the transit time of electron, how much time an electron can take from moving from, let's say, channel is here, from this region to the other end of region, this region. The time taken will be the gate length over the saturation velocity, assuming the electron has reached the saturation velocity, because that is what is basically given from this plot. All right, so now what you can do is that you can obtain this particular transit time. What is the gate length? It is 500 nanometer, 510 to the power minus 9. Saturation velocity is 3 into 10 to the power 7 centimeter per second, which is 3 into 10 to the power 5 meter per second. Yeah, so this is 3 into 10 to the power 5 meter per second. So this will be 5 over 3 into 10 to the power 2 into 10 to the power minus 9 minus 5. So this will be tau. So this should be in seconds. So this is 3131.66, 1.66 into 10 to the power. This is minus 14 plus 2. This is minus 12. So this is 1.66 picoseconds. So this is tau. And now you can invert it 1 over tau. You get the unity gain frequency of this particular intrinsic to the HEMT. And I guess the value should be, how much would it be? 1 over 1.66, 1 over 2, it should be close to 0.5. So 1 over 1.5, this is 10 over 15, 5.2, 5.3. This is approximately, yeah, that should be the value of it. Approximately around 0.4 to 0.6. That means somewhat like 50, between some 30 to 50 gigahertz will be the answer of this question. Yeah, that should be, if you calculate it carefully, you will get that particular value. But this is the particular reasoning of this question. So the important thing is this intrinsic factor here, which is basically intrinsic to this particular device. Okay. the velocity field. Okay, we're done. Just give me a moment. Okay, now we have to moving to the question 13. We have to consider an AlGaN HEMT which has a breakdown voltage of 120. The drain can be biased safely at. Okay, now what determines this safe bias? What determines safe bias? That means if you have a breakdown voltage of HEMT at 120 volts, then what is the safe voltage you can apply to the drain bias? Okay, so you see about the curve. It's all about the it's about drain current versus the drain to source voltage. You know that it looks like this. This is what I have been plotting in the previous things. And VGS, let's say this is VGS equals to -1, this is -2, -3, and -4. The channel is pinched off. That's what I've been talking about. And this region is basically this is a linear region. This is a saturation region, and you want to work in the saturation region because that's going to give you the gain, the transconductance, and all other things. Okay, so this is the knee voltage. So what is basically determines the safe drain current limit? What determines it is that how much drain voltage is swinging around a particular value. So whenever you have a drain voltage, because this is the drain axis, this particular value is the maximum voltage, which is the breakdown voltage you can give. Okay. Now you have to apply the voltage at the drain, which should be swinging between these two values only. This is the RF voltage at drain. Okay. This is the maximum swing you can apply. Why? Because if this black region goes beyond this, it will go into linear region in this region, and it won't give you any gain. So this is bad. If it this thing goes above, this will go into breakdown region. So it will break down the device. Your device will break down completely, and it will be a catastrophic damage to the device. Huge current will start to flow. So you want your drain bias to be between these two values. Theoretically. Practically, you want it to be around this thing, small, so that it should not touch the breakdown and it should not touch the knee voltage. Okay, because every time the drain voltage will touch the breakdown peak, every time the drain voltage will touch these peaks, there will be stress in the device. Although it will not break down because it will be for a moment, for a very brief time, the voltage will peak at this particular point towards the breakdown voltage. But there will be stress in the device, which will be basically the breakdown stress or the thermal stress and other kind of stresses. And that is with time going to age the device. So it's a reliability problem. Okay, so it's a reliability problem. So that's why you want your drain bias swing to be very small compared to that of these peak values, compared to that of these peak values. Okay, so the approximate limit is that the drain bias should be half of the what should I less than the half of the breakdown voltage. If this is breakdown voltage, it should be swinging around this value, which is almost VBR divided by 2. So your drain voltage should be less or equal to VBR divided by 2, or rather it should be less than VBR divided by 2. So accordingly, the safe bias for it will be 120 by 2, which is 60 volts. So VD should be less than 60 volts is the safe limit. So and this is the correct answer, and this is not the correct answer because it's exactly 60 volt and it will be touching the breakdown voltage. No, it will be I should say not touching. It will be almost going towards the breakdown voltage, which will cause stress on the devices. Okay, so this is something called as the how the drain voltage swing should be, and there should also be current swing. How the drain current should vary. If you have let's say you have a drain current swing which is looks something like this. Okay, so here this is drain current swing. The drain current here, if it overshoots this peak, it will go into the maximum drain current value. It will go into a very huge current value, and if it goes below this current value, it will go into the pinch off region. So So there will be clipping of those peaks. Okay. So that's why you want this particular current also to be around this particular thing in between. So that's what basically gives you the something called as load line, which may look something like this. Load line is you want to bias your device around this point. This should be exactly here. This should be exactly here. So this is the load line of this device. This is something called as Q point with some VD and ID. Okay, yeah, drain current and drain voltage. So this is something called as quiescent point, or this is the load line basically. It shows you where you should be biasing your device in order for the safe operation. It should not get clipped. It should not get the device under stress. It should not get device in a pinch off. It should not get device in the linear region. It should remain in the saturation region because this is the region you want the device to be in. So that all of your swings of the voltage, which are in the microwave frequencies, they should be here in this region. You don't want them to escape into breakdown or the linear region. That is the concept of this question. Okay, now what else? In handheld electronics, so this is a quite a theoretical cakewalk question. The drain bias is limited by, yeah, it's quite simple. In handheld devices, one of the biggest problem is the battery supply. Why? Because the power amplifier sucks in the power from the battery because it has to transmit electromagnetic waves through via the antenna into the space. So it has to boost the signal. So whenever it has to boost the signal, it takes a lot of power, huge power from the battery. So that is basically one of the critical roadblocks in making high frequency devices, handheld high frequency devices at particularly throwing a very high power. So you have to have a battery which is huge, but you cannot use huge batteries in the handheld electronics because people won't be glad with it. People want smaller devices, faster devices. So that's why designers and circuit designers have to push the limits, and that's what is basically happening. People are pushing the limits, and we have reached almost a saturation stage where the cutoff frequency is almost limited. It has almost saturated approximately 5 gigahertz. I'm talking about CMOS, not the microwaves. I'm talking about CMOS. In the microwaves, you don't have the limits. In the microwaves, the limit is maybe there is 100 gigahertz have been achieved, 150 gigahertz has been achieved, but maybe we don't know about it because this is used in the defense radars or maybe jammers, anti-drone jammers or drone technologies. These particular things have been used there. But if you talk about CMOS, then the cutoff frequency is basically saturated because due to different reasons, because of the channel length, because of other things. But problem here is that if you have a limited battery supply, you cannot make arbitrarily high power amplifier, or you cannot give, I should say, huge. Your power amplifier cannot take huge power because it will drain out the battery immediately, and that is the most power hungry block. I should say power. Let me use this. It is the power hungry block in the in entire trans receiver system, TR system. Because you see that whenever we are talking, or whenever you send a message, let's say SMS, it gets converted into some signal, a carrier frequency, carrier frequency and the envelope frequency. Then that is basically transmitted via the power amplifier and given to the antenna, microstrip antenna, that throws it into the space. So throwing it into the space using the electromagnetic waves, it uses a lot of power, and this is the region where highest power is thrown out of your particular system, and that power comes from the battery itself. Okay, that power comes from the battery, and that is why the radiation levels basically are important. So what are the radiation levels that are coming from this particular device? They are that has to be under the particular limit, and even if I talk about, this is at a I should say handheld device. Now, if you talk about, these microwaves are basically sent to the air to the nearest base station, which is basically a tower. So at the tower, something has to receive it in order to process it further. And when it, let's say, there is one more tower, it basically transmits these microwaves. So this part where it transmits the microwaves is the most power consuming part because it has to transmit those microwaves into the free space, most power consuming. Okay. And And this is the only part where the radiation levels are huge. Or I should say the microwave power levels are huge. Microwave power levels are huge. Okay, so if within the almost the radius of almost 100 meters of the base station, the power microwave power levels are really huge, and it's almost advised. Even the people know in communication sector, people know that almost in 100-meter radius, it should be, I should say, the population should not be as dense. Okay, so that's particularly preferred because at this particular level, the base station level, near within the 100-meter radius, the electromagnetic wave power is very huge because it is almost started to begin to generate the electromagnetic waves. So these are the electromagnetic waves. So typically we try to keep power as minimum as possible, but that is what happens after it releases the antenna. But at the antenna level, the power levels are huge, so that can have some detrimental effects. Maybe people are not accepting it, but internally most of the people know in the community that within a certain radius there are huge power levels in the base station. Okay, so that's a different kind of a concern. Let's not talk about that. And what else is there? The ratio of dislocation densities in GaN on silicon and GaN on silicon carbide is, so there are two things. One is you can make a GaN using a silicon substrate, but there will be huge dislocation densities here, because there will be lattice mismatch. What you can do is that you can use a GaN, you can use aluminum nitride nucleation layer, and then you can use silicon. This will reduce the mismatch. Okay. And then you can use gallium nitride, but you can use silicon carbide interface. So these are the other options. These are some of the options for the basically using the substrate. But it's mostly that there is a huge dislocation densities because of lattice mismatch here at this particular position. If you use the silicon, if you use gallium nitride over the silicon, so the ratio of dislocation densities for GaN on silicon to GaN on silicon carbide is almost 1,000. It's almost huge. Okay, even it may be greater. Let me check what they have marked as the solution because I don't want to conflict with the solutions. Yeah, now they are mentioned the 10 to 100 almost, but it can be almost of the order of 1,000. It depends upon the concentration and other factors, how the fabrication has been done. So as per them, the answer is this, but it is that the concept is that the dislocation density here in case of the GaN on silicon is greater than GaN on silicon carbide. So GaN on silicon carbide forms a better contact here, better contact. So it reduces the dislocation densities. Okay, now what else? N-polar HEMTs are advantageous over gallium polar HEMTs because, so what is this N-polar? What is this gallium polar? If you have a, if you have a, let me try it. If you have a sample, gallium nitride, a disk, which is a sample, uh, so you know that if you cut a cross section of it, and if you draw the front view, you have the, why am I rubbing this thing? Let me rub it partially. You draw the front view, this will have some thickness, which is the gallium nitride thickness. Then this particular side, which is the top side, it behaves as a positive, and the bottom side behaves as a negative. Why? We have discussed it so many times because this is a polar material. It's a polar material. There are polarization fields inside because of the electronegativity difference between the gallium and the nitrogen. This is slightly negative, this is slightly positive, slight negative, slight negative, slight negative. So accordingly, you can have the polarization fields and the electric fields. This will be the electric field, this will be the polarization fields. That's what we have been discussing from so a lot of previous classes. So because of these polarization fields, something called a spontaneous polarization, this top surface behaves slightly as positive. This bottom surface, which is the bottom side of it, behaves slightly as negative. So this is called as something called as gallium polar. So if you make a HEMT out of it, you will get a HEMT something like this, which will be AlGaN, and you will be having a gallium nitride here, and you will be having 2 deg here. So this is equals to 1. This is 2d electron gas. This is Fermi level. So this is the gallium polar structure. If you reverse it, you get a nitrogen polar HEMT, which is N polar HEMT, and it's very efficient, and it has been proven that N-polar HEMTs are very, I should say, significant improvement in the performance of the performance of the HEMTs. This is almost like reversing the entire thing. So now you have a, this is the top, this is the bottom, this will be negative, this will be positive. So this is something called as N-polar. And if you make a HEMT out of N-polar, it will be opposite. It will be like this, like this. Now you have the AlGaN barrier on this side, you have GaN here, 2D density is here. This is the Fermi level. You have the 2D density here. Here you have the 2D density over this side. And and you know that the centroid of this 2D is approximately 2 to 3 nanometers away from the interface in AlGaN. Similarly, here it's 2 to 3 nanometers away from the interface. So what happens because of it? You know now the gate is on this side. The gate is on this side. Now in this case, the 2D density is closer to the gate, so I have a better control compared to that of this thing. Because the overall distance from gate this point to this centroid will be large than compared to that of this point to this point. So now you have reduced it. Also, you have a better confinement here because of this huge barrier. You can directly control the channel now. You can deplete it, you can play with the channel, and accordingly you have the better control and better performance. So what are the options? Lower contact resistance, better carrier confinement due to back barrier, higher breakdown voltage due to back barrier, higher gate delay. So this is not, so the better confinement is there definitely. And I guess the higher breakdown voltage due to back barrier should also be the answer of this question. But better confinement is definitely because of this particular back barrier. This is something called as back barrier. It was discussed in the first question also, AlGaN back barrier. So it almost reverses the entire thing. And because if you see this particular, if you zoom this particular region in the gallium polar HEMTs, if you draw the 2D, 2 deg, this is Fermi level, this is n equals to 1, this is 2D electron gas, 2D electron gas. This centroid is towards this side. I should say, what should I say? What should I, how should I draw it? The peak of this centroid is 2 to 3 nanometers away from interface. That's what I discussed. So it's almost towards the gallium nitride end. But for the peak of this here, centroid is towards the gate end. Okay, so you can have a better control over it, and again this particular barrier can confine the carriers in a much better way. So you have a good confinement here. Let me draw it like this. You have a better carrier confinement at this particular location, and this leaking part will always be there. There will be some leaking part of the wave function. So for in order to see this, you have to solve the Schrodinger and you have to compute the wave function of it, wave function of 2D electron gas. Okay, so that is about the n-polar and gallium polar HEMTs. And right now, this n-polar HEMT basically is a quite hot research topic, and people are working on it, making the n-polar HEMTs with this reverse polarity. And definitely, they have to change the architecture of the device. Maybe I guess Intel has recently come up with into 2018 or 2019, they have come up with the devices. Many more groups have made these n-polar HEMT high electromobility devices, and they have shown a better performance in terms of power efficiency, in terms of high frequency characteristics and current voltage characteristics. Okay, all right. So we are done with the question quiz session. I didn't discuss much of the topics in today's session because there were almost, I guess, 6 lectures this week. So it's almost impossible to cover it in 2 hours. So that's why I decided to almost discuss the concepts in the questions itself, briefly discuss the concepts initially, and then went into the questions directly so that I can discuss the concepts in the questions itself because they are important and otherwise it would take a lot of time. Okay, so we are done with this. If you guys have any question, I can see there's only one person. If you have any question, then you can ask. Otherwise, we will end this session. Hmm. Yeah, yeah, exactly. I think almost similar concepts will be asked in the exam. Just like these, most of the time, these numericals, they are very important for your exams. Okay, maybe they might change some of the values. They might give a different critical field, different velocity, saturation velocity, and you might have to compute the similar thing. Similarly, questions like this, they can be directly asked, or certain values may be changed, but they are really important. Okay, thank you.